Hello, my name is Alex, and today we're going to talk about redirecting attacks to honeypots for advanced payload detection. A little bit about me. I have finished the Faculty of Automatic Control and Computer Science, both the Bachelor's of Engineering and a Master's degree, and I'm now first year PhD student. I've been working at Bit-Sentinel for over 3 years, approaching 4, as a penetration tester, and I also made challenges in conjunction with CyberEdu for competitions such as DCTF that's running now. Before we can start solving anything, we have to find a problem. Advanced persistent threats are threat actors that reside in the organization for a prolonged period of time. They usually send personalized payloads to an organization to exploit it for a certain reason, be it political, financial, or other. Some problems that we have to find and solve where to block an attack. We can block it too early and then they can try to obfuscate payloads, and we can block it too late after it made impact. A differential between intrusion detection systems that detect attacks asynchronously and intrusion prevention systems which block attack as they happen. How to keep up with the attacks? You have 3 main objectives: rule detections, such as regexes or tokens, behavior analysis, such as this employee is doing something that he shouldn't be doing, and also machine learning if we're going to talk about behavior analysis. Then we can also think about what if we want to deceive the attackers. Maybe they can give us the payloads directly to ourselves without causing impact. Well, this is what honeypots do. However, problem is that they're usually not representative for our technologies that we use. They usually are pre-made with some technologies that are specifically vulnerable to be attacked, to take away time from the attackers. Let's talk about a bit firewalls and honeypots very fast. Firewalls have multiple generations historically. At the beginning, they were just packet filters that will look at the TCP/IP stack. Furthermore, they evolved to stateful filters that would also look at the TCP session and add more packets to the traces. Then next generation firewalls included intrusion prevention systems into them, blocking attacks as they happen. And if we can swap the TCP/IP stack, we can see that firewalls evolved to look more onto the application level. Honeypots, on the other hand, as I said, they are systems specifically designed to be attacked. They can be categorized into low interaction honeypots that usually have a static application, and high interaction honeypots that allow attackers to maintain sessions and give a more presentable target to be attacked, such that they take more attention. Intrusion prevention systems, as I said, in next generation firewalls, are systems designed to block attacks. Some pros, well, if the rules are right, we can block attacks before they can happen. However, blocking attacks is not usually the best thing you can do as soon as possible, because then you have a problem. Attackers know that you have an intrusion prevention system behind you. If they found a vulnerability, they're gonna try to obfuscate their payloads to exploit the vulnerability. And now we have a problem that defenders try to fix the vulnerability before attackers can execute payloads. A solution that we can think of, how about we migrate attacks instead of just dropping them, such that we take more time from the attackers before they can realize that they're no longer on the target system. Furthermore, what if we can make attackers send more personalized payloads, making systems that look just like our production systems but without sensitive data? How we can do this? We will need a base. For this, I propose software-defined networks that allows programmable control of the network. That is, you code, for example, a Python script that controls every switch. And for that, we break the network into 2 planes. The control plane, where the controller resides, or multiple controllers if you want to have backup, and the data plane, which contains switches that are very, very simple, that have some tables that you populate from the controller to know what to do with the traffic. Rules that you can install on the switch can be proactive or reactive. If the switch doesn't know what to do with the packet, it will usually redirect it to the controller such that the controller can take a decision what to do with it. Now let's go back to our problem, state-of-the-art that solved some of the problems on redirecting attackers to honeypots. At the network level, we have OF soft switch that proposed a more advanced OpenFlow switch that will also use arithmetic operations to recalculate the TCP IP sessions, the sequence and acknowledgement numbers. Furthermore, HoneyDoc proposed let's keep the software-defined network standard as it is, and let's just recalculate the TCP IP sessions on the controller itself. Then some people thought, what if we leave the network layer as it is and we recalculate it at the process level? And one research found out that Linux can do this with a TCP repair function present in the kernel. It basically can recalculate sequence and acknowledgement numbers such that you can make the traffic look smoothly. Furthermore, MF-Honey tried to redirect attacks from low interaction honeypots to high interaction honeypots to better lure attackers to continue their persistence with CREU, which we will talk about a bit later. Back to our problem, how to keep up, we still have to think about that, but where to block attack, we propose to relocate attacks instead of blocking them. That way we can get personalized payloads. About the honeypots, well, now we can relocate attacks. However, the research so far only solved the problem of TCP IP communication, the sequence and acknowledgement numbers. What if we have an application? The application layer has to be remade as well. So if we have, for example, an energetic server that talks with a client, anything that is stored there will be lost. Only the TCP IP session will be kept. So we have to find a way to solve that as well. Back to the state of the art. Intercept Plus is a research that proposed creating honeypots out of your own production system based on VMs. It will basically create a VM clone of your production server with QCOW embedded in it, and basically the attacker will be redirected using software-defined networks to the new server. That will be the honeypot. However, if you can think about it, you will also migrate sensitive data that is stored in the environment of the virtual machine. Then SendNet proposed, let's do not use the entire virtual machine, let's just migrate containers. They use the CREU, again, to migrate the containers. And you'll still migrate some data, such as API keys present in your production environment. So what we thought about with counterfeit, let's just migrate the process that the attacker is communicating with. That way, all our environment stays the same. The only thing that will be migrated to the honeypot will be the process. Let's talk about CREU, because we mentioned it frequently. It is a Linux application that uses user space features to migrate processes. It basically freezes a process into cfreeze group, then injects into its payloads, and makes a dump of the process that could be later restored, either on the same machine or another machine. What we need for our infrastructure to work, well, we talked about the SDN controller, but we'll also need an auxiliary system to handle the migration of the process. We want to migrate the process from the server to the honeypot. And we thought about how to migrate it securely, and we added encryption. Also, the migrator will be stored on the control plane. If we zoom in a little bit, what will happen when an attack will start? Let's say on the blue side, the client communicates normally without sending any payloads, any malicious traffic. Also, attackers in a HTTP server must do the TCP handshake first before sending any payload. So that will be the blue traffic. Then, when a payload is sent, the red one, the SDN controller will be notified, will find some payloads, then we'll start the migration process. It will tell the migrator, hey, I have an attacker from this IP and this port, migrate the process that he was talking with to the honeypot. Migrator will identify, in our case will be the first process, and will migrate it to the honeypot. Then on the networking side, we will send the attacker to the honeypot. To further optimize, we'll also install some rules in the SDN switch to send automatically the attacker on future packets to the honeypot itself, since we already know that he is malicious. Some communication considerations, since we talk about detecting payloads, we'll propose that we split traditional detection methods into two. Ingress detection, that is traffic coming from the attacker to the server, will scan them from payloads, such as OS execution commands, so on and so forth. This kind of traffic we will migrate to the honeypot. That's simple. However, what happens if we detect that our server is sending sensitive data back to the attacker? Well, in that case, we cannot migrate the process because it will still contain sensitive data. In that case, we will want to drop the communication and just send the attacker, redirect him to the honeypot to talk to a new process. He will see that, hey, the TCP handshake did not complete, something is wrong, but he will not get the sensitive data. A little bit about sockets. To identify a socket, you have a 4 unique tuple. You need a source IP, destination IP, and a source port and destination port. When you create a socket, you have 4 or 5 stages depending on the operating system. You create the socket, you bind it to the operating system, you listen and accept data. However, the binding part is interesting. Previously, servers would bind to a socket, and that socket will listen to a port that will be only for that process. You cannot bind more processes to that specific port. Until Linux started introducing the SO reuse port flag. Since the 3.9 kernel, you can have multiple processes listening to the same port, and the load balancing itself will be handled by the kernel. So the operating system will look, hey, this is the tuple, I'll have to send to one of the processes that is listening to this port with this flag. So that way you can have multiple processes listening to the same port. What if we want to migrate a process that does not have SOE use port? Since we already have some processes listening on the honeypot, and some processes will come from the server. Well, if it doesn't have SOE reuse port, then there will be a conflict. Well, we can just force them to have it. We can overwrite the library files. Before the socket call is called, we'll just override the function, add the SO reuse port function to the executable, and then we'll send the socket back. Some metrics we did. During the crew migration and the crew restore process, we noticed that it is very small. However, the secure transfer of the process dump takes considerable amount of time, and it's also dependent on the dump size. For example, on a flash server that uses a lot more memory than an Nginx server, it will take considerably more time, almost half a second, but on the bright side, they're still within network timeouts. So a client trying to connect it will not experience the timeout, automatic timeout. A very short demo. We'll start by starting 2 Nginx processes that will use the SO reuse port functionality using a configuration. Then we'll also start 2 Flask servers, Nginx servers first, with the LD preload mechanism to overwrite the socket to be able to use the SO reuse port. Otherwise, you couldn't start 2 Nginx servers as different processes. Also the same with Flask, and this could be added to any kind of process. Then we'll do the same on the honeypot side, which was skipped here. Furthermore, if we think that we'll migrate processes from the server side to the honeypot, then we need to have a way to clean additional processes. And this little script just does this. It checks for the listening processes on specific ports, and if it gets new processes, then it waits for them to close all communication. Then it just kills them. It means that the attacker terminated the communication with the server, and it could easily kill it because it can remake a communication to an existing process on the honeypot. On the switch and controller side, we'll have to have two interfaces, one for the client side, one for the server side, and one for the honeypot side. All these three interfaces will then need to be connected on the OpenFlow switch. We'll also identify in which way the attack will go by the physical, in our case, virtual port that will be redirecting the attack. Okay. Also, we used OpenFlow in the background. Then we'll also have to start the SDN controller. We coded it in POX controller. It is a bit deprecated. We want to migrate it to ONEOS. It will also show when it's connected to the switch itself. The switch connected. And now we'll also need to start a migration server that will listen from the SDN controller when an attack is happening. It will need to know which was the attacker, where the attack was coming from. Everything set up. Right top we have the migrator server. Right left we have the switch and SDN controller. Bottom left the garbage collector from the honeypot. And bottom right it's the attacker himself. First of all, it will send some curl queries to the server, some legitimate queries without any payload. First to the Nginx server. That will be sent successfully, nothing happened. We will also receive repair replies a bit late because they were pre-cached during the registration. Those are the repair replies coded in the SDN controller. We can also try the Nginx server, Node.js server, and Flask server. They all work correctly. However, on the honeypot side, I forgot to start the Flask server, as we'll see very shortly. Now we'll start an attack. Multiple things will happen. First of all, about the attack, it's just a simple query for a path traversal. It will not execute anything maliciously on the server, but it's an example of detection. We'll see that the controller detects the attack and the migrator starts the migration. Also, the registration was 2 times slowed down. Migration is over. The response was given. Also, the honeypot garbage collector killed the transferred process because also the attacker no longer communicates with it. So now the attacker is sent to the honeypot himself. We can also try to send a legitimate request back to the Nginx server. We will still be on the honeypot from the attacker side, and anything else we do maliciously there will be stored on the honeypot, no longer having access to our server itself. And as I said, I forgot to start the Flask server demo. We talk about research, not trying to sell you a product, but also about our research itself. We will also talk about limitations of our infrastructure. First of all, encrypted traffic. If we think that we can store certificate, for example, a TLS certificate on our server, then if we migrate that process, that certificate will be also migrated to the honeypot itself. So we cannot store that because an attacker can get access to it and decrypt client data. To counteract this, we'll need a decryption proxy before the servers. That's an easy fix. Multi-process migration, this is the next stage that we want to do with counterfeit. Detect process dependencies and migrate process dependencies themselves. Still migrate processes, not entire environments. Also, NAT client. If you consider IPv4, we know that IPs are shared from internet service providers, multiple clients containing the same IP. If we block attacks based on IP, then we might also block some legitimate clients, which might be an issue, but this is a general issue with blocking IPs. Also truncated packets, we need to add some memory to the SDN controller to see more of the attack, more spectrum of the attack, such that we can detect attacks themselves. But this is also some consideration, how do we want to detect attack? Regular regexes or regular tokens? Then one thing that we have to take in consideration, our infrastructure blocks server-side attacks. If an attacker sends, for example, to phishing attacks, cross-site scripting payload to a client, then if we migrate the process, we do nothing because the execution will be on the client side, on the client's browser. So this does nothing. In this situation, we propose that you should just block the attack and not even migrate it, since you might migrate a phishing victim. Next steps we want to do with our infrastructure. Well, since we automatically migrate attackers to a honeypot, what if we can automate the entire process of grabbing personalized payload detection and intrusion detection and prevention system rules? We'll need a rule extractor to monitor attackers' intent. Maybe he wants to escalate privileges, so on and so forth. Then once we detect, we extract some rules, we can use a CI/CD system to automatically test those rules against legitimate and not legitimate traffic to integrate it automatically in our infrastructure. This is the proposal we're trying to do with our project, automating defense. In conclusion, we redirected attackers live such that they no longer have access to our infrastructure, our sensitive infrastructure. We did it transparently. The attackers does not see that anything is wrong with the traffic. It's just a small delay that could be ignored, especially in scanning situations. It's still within network timeout limits, under a second, even for a Flask system. The infrastructure is scalable. We can migrate multiple attackers that work on the same server to multiple honeypots that are in the same infrastructure. Since we have garbage collectors, we can do that indefinitely. And we can extract customized intrusion detection and prevention system rules, since the attackers still target our infrastructure as it is a system. The same backend technologies, the same code. About the code itself, we might want to obfuscate it on the server side, but this is a risk that we have. That being said, if there are any questions, thank you for the presentation. There is here a question.
Thank you for the presentation. The counterfeit honeypot is now it's designed for Linux servers. If I have Windows servers in the infrastructure.
Yes, it will not work. So far, the Creo technology only works on Linux. You'll have to write some kernel modules to replicate the same technology on a Windows server. So anything running on Windows will not be migrated.
Thank you.
Hi. Thank you for your presentation. So when you mentioned the time for migrating a process from the server to the honeypot, you said it's done within the standard network timeouts. However, if a process has a large virtual memory allocated, how long did you expect, or how long did it take in your sense to migrate such big process? You mentioned Flask, but I imagine there are several servers that will have a greater virtual memory, and I expect to take longer to migrate.
Yes, very good question. Well, in that situation, we have to think about how to optimize the transfer of data. The biggest bottleneck right now in our infrastructure is that it takes a very long time to transfer a process dump from the server to the honeypot. Since we already have a secure communication, we use SSH in the background. Also, the SSH server was continuously being run with control groups, such that you do not need to make the SSL handshake each time you migrate, but still it was a considerable amount of time. So we need to find some ways to transfer bigger processes.
Okay, thank you.
Thank you.
In your production deployment, do you integrate this with a web application firewall, let's say? The rules?
Well, about this, I saw multiple research that also mentioned including Snort in the control plane to integrate with intrusion prevention systems. However, our infrastructure was basically coded an intrusion prevention system inside the controller, inside the Python controller. The rules that we made were specifically targeted. It is not production ready because you'd have to connect with a real prevention systems that can parse rules, for example, YARA rules.
I see. Thank you.
Thank you as well.
Hey there. There was a slide back with the communication between the attacker. Yeah, keep going.
This one?
No, more. Between the direction to the honeypot.
Okay.
I was curious to ask if we keep the communication when we first see the first payload, and we keep the communication only with the honeypot. Shouldn't we have a controller to redirect the legitimate traffic back to the server?
Yes, in this situation, you have to think how you can send the legitimate traffic back. Again, one limitation that we have, we block by IP. So if there are multiple people using the same IP, clients will be affected. In this situation, with the SDN controller, we have rules that expire. Such that when the attacker no longer sends malicious traffic, the rules will expire, the traffic will be sent back to the server.
Okay, so there would be a time frame for that communication between the attacker and the honeypot?
Well, we did not research it. Right now I think it's 2 minutes, if I'm not mistaken. But it could be set how much you want, because on the SDN controller you can set timeouts for this. Also, we can also add to the infrastructure asynchronous intrusion detection systems to detect payloads.
Okay, thank you.
Thank you as well. If there are not any questions, thank you.